Hey, Dylan. Oh, where am I? Where am I? For some reason, I guess it's my headphones. I don't know. Hey, Dylan, how you doing? Let me get the thing working. You were talking about some web pages and stuff. I feel like I'm slightly cut off right here. Oh, look at that. There we go. Perfect. Let's see right here. Forgot to ask in class, do you know any of the packages places to look on the internet to interact with a web page? I have a tiny bit of experience with Google Sheets, G Sheets. So did you know there's the G Sheet web page or the G Sheet? I feel like the headphones. I don't know. There's G Sheet. So that is one way. Input, search term, and then click download button is a bit beyond my current coding knowledge. I'm not sure. So yeah, don't worry about that too much, I would say. And for those who didn't see, we did get, so if you were watching last office hours, let's go check that out. There is G Sheet, Dylan, so we could take a look at that. Let's talk about, we'll start up some time series right here. But we got it figured out. 1 minute and 10 seconds in. So BAS 475, time series analytics. But what are people wondering? Dylan, questions? Great stuff. And Parker, so good to see you. Is Mubot awake? Let's find out. We did get this graphic finalized. I feel like we should tweet it out. But start of a New Girl season, search frequency with season 1, season 2, season 3, season 4, season 5, 6, and 7. And we can even remove these off, but we got it working. I've used GC some. I wonder if there's for the Google Trends polling. Yeah, so we could look into that. Let's think right here. The Google Trends polling got so many things open. So the Google Trends polling. Let's see. So Google Trends R package. Google Trends. G Trends, perform and display Google Trend queries. Right, there's a package right here. So the G Trends package. So it looks like someone's created a package for this. October 24th, 2021. So very recent package. It's on GitHub. I don't know if it's in the repository yet, but we might have to go to GitHub to get this. And so we'll start off a new thing right here. And let's do install.packages. And the answer is, it looks like it's there. There we go. Yeah, we already got this. We're good to go now. Look at this. Libraries, G Trends, we got it. It was made under an older version of R or newer version. I don't know, one of the two. Version 1.5. Works on R greater than 3.5. Let's see. Let's look at, definitely going to use this. Definitely, yeah. You could, oh my gosh. I swear, spring break ended and I'm still just, everyone is tired. It's, man, I'm tired. I'll say that much. G-Trends. Well, there we go. Might be able to grab it. How do you use the G-Trends function right here? I love it. It promises it's there, but is it there? It promised. Keyword, there it is. Time today plus 5 minus 5 years. 5 minus years, I think. So those are the defaults. We can probably just do a keyword like Google Trends right here, a keyword such as like stat 201. We were doing this earlier. And let's see what it does. It's using all the defaults. It looks like it's searching out there to the web or doing something. And there it is. And it might have created that in the environment. It might have said, did it create a whole bunch of stuff? Well, those are my models I created earlier. So I don't think it's stored. Whoa. What did it grab? What? What is this? This is cool. Stonks. That'd be interesting right there. So let's store this as a search right here. All right, let's see what happens now. So this is grabbing a lot, Dylan. This is pretty intense. So this is really cool analytics on whatever we're getting right now. Let's see what the search got. It is a list of stuff. So here we go. Invest over time. What? Wait, what did I create? Interest over time. So let me go search interest over time. And let's take a look at what we got here. Oh my gosh. Oh my gosh, so cool. So here's the interest over time right here with different weekly grabs on it. So hits 27, keyword. So is it grabbing more than 100? On the world, time minus 5 years. Today plus 5 minus years. So it should be going off 5 years minus. And let's look at, so that's the interest on how much it was searched. Cool. And we could break it apart into other things like other regions. So we could do comparison. Interest by country. No one's searching for it outside the US, it looks like. We have a bunch of NAs, missing data. So Canada. I don't know why. That one's not so interesting. Interest by region, nothing there. Interest by DMA. I need to make this wider. It's sorted, I think. So we're only going to see the data at the start. No, it's not sorted. Oh, Knoxville TN. Well, why is Knoxville so high? And yet it has no data for it. Almost looks like a G-Rub or something. There's code that looks like to me. Interest by city. Well, those aren't cities that I know of near us. By topics. This is not, okay, here we go. This is interesting. Reddit? Like we're rising with Reddit? Computer science, Quizlet. Oh, yeah, Stat 201. So we are it looks like we're the number one when it comes to Google. We're Stat 201 is the number one. The related topic to Stat 201 is people are looking up University of Tennessee. So we are the Stat 201 in Texas A&M falling behind, but that is cool that the highest related search term for Stat 201 for the midterm, would we need to know how to calculate 6 by hand with a calculator for 320, right, Chase? 320. We are not going to, you're talking 320, right, Chase? Correct me if I'm wrong. I'm 99% certain. You're not going to calculate a lot by hand by calculator. There is some calculator work, but the majority of the work is conceptual, interpretations, stuff like that. But yeah, so the majority of the work is like conceptual interpretation stuff. Yeah, no, good question. You do know how to you do need to know some calculator work. You do need to know output, but like the biggest things you might have to do, like, do I have an ANOVA table still up here? That's not a good ANOVA table. Oh, because I think I have the original model. Oh my gosh. Well, let me change this. Watch this. We're gonna go back to our original stuff right here. Let's talk about the 320 midterm. That's really cool right there, Dylan. So we'll take a look at that. So you need to cover. Oh no, that's exactly where I was going right there. So let's go ahead and chase and let's start off such a good question right there. Do we need to know how to calculate R squared? So BAS 320 midterm advice. Let's go take a look at some midterm advice. Here we go. So the midterm isn't calculation heavy as in like you're going to do advanced calculations, but the midterm is important to know how to do calculations that are kind of like conceptual calculations. So if I were to ask you the following, calculate R squared from the following. So we're going to make a model right here, and we're going to calculate R squared from the following model. So with this, calculate the R squared of this model. Could you do this? Chase, what are your thoughts right here? Things like, yeah, awesome, right? Good work, Dylan. Excellent work. And the G trends thing looks pretty cool right there. Like that's a whole realm of possibilities. That's a whole wide world open up, whole new world for us. So what could we do right here to calculate R squared from this output? Calculate R squared from this output. How would we calculate R squared from this output? Any idea, Chase? What do we do? What is R squared? R squared is the percent of variation we explain in the Y variable. So conceptually, there's a lot of things going on right here in this table that would help us calculate R squared. So we need to know the percent of variation we explain in the Y variable, which is mathematically on here. So questions right now, Chase. We'll start investigating this and we'll calculate R squared from this. And this is kind of one of the key things to calculate. You got it, Chase. That's worth 100 points right there. So Chase, where's the reduction? Where is the amount we've explained? That is the correct answer, Chase. That is the mathematics for it. So then you have to find what is the reduction, like what did we explain right here? And so Chase, you're on track. If you know that right there, that's like, okay, the R squared is how much we've reduced the error by over the naive's original error created. So this table has those numbers for us. We just have to know which numbers we're looking at. To be like, oh, that number means this, that number means this. Like, this is what we've explained. This is what we haven't explained. The reduction, you got it right there. This is the reduction And we could store this right here to say the reduction. Now, it's with the x variable. I cannot spell. This is the reduction. Now, what is the naive, though? So you're missing one last component because Chase said we need to solve the equation, the reduction, which is how much the x variable explained in the sums of squared. And then he said we need to divide it by the naive's sums of squares. So whatever the naive model had. So the naive model is a no variable model. I could make a no variable model, but on the test, you might not have that output. You might be stuck with this output and not know what the original model had. We can figure that out from this. So think about this. We have what is explained and we have what is not explained. And that's how much there was to explain. So we have what was explained and we have what was not explained. And that would be what there was total to explain to begin with, if you put them together. So what are your thoughts, Chase, on how would we find the amount of variation starting out with? How would we find the total variation there was to begin with? How would we find the total variation there was to begin with? How would we find the total variation? It's all right if you say, I don't know. I don't know is a great answer. I'll give points for I don't know. But how would we find the total variation there was? Do you add up the... I think you just said it. Right answer. 100 points, Chase. You got it. We would take this right here. So let's do the naive. Is the this plus this right here. You know what's really great? If you do examples like this and you practice, you would say, well, that's the r squared. And check it out. That value right there is the r squared. So you just did it. You just found out that the naive is the total variation there was, whether what's left over in the residuals or what was explained by our model. So the naive would be like what we explained and what we didn't explain, because our model is going to explain a portion of the variation, and that's the reduction. And then what's not explained is left over in the residuals. So if you put them back together, Poggers, I love it. Love it. Some Twitch talk right here. But yeah, you just did it. Great walkthrough, Chase, right there. So that is something we might ask you to find, like find the r squared with this ANOVA output. I'm not so much interested in the other values. They're not too crazy to find. This value right here is if you just divide this number by 30. So if you take this right here, we'll show it on the same screen at one time, and you divide it by 30, it's because it's on average per degree of freedom. So there's decimals we don't see, but this is on average. The F statistic right here is just the ratio of the two numbers. It's sometimes called an F ratio, but that value right there is the ratio of these two numbers right here. It's the kind of like how much do we have with our model over what is left. So we want the F ratio to be large, and that will lead to a smaller p-value. Conceptually, we should know that larger Fs lead to smaller p-values. Smaller Fs lead to higher p-values. And when you have a larger F, it's because your model is doing more sums of squares. Your model is accounting for more variation, making the F statistic larger. It's about as much detail as I can go into on this. We're not going to calculate these sums of squares. We're not going to calculate this sums of squares. You could have to calculate this. It's just 1 divided by this, so it's always the same for a one variable model. And we don't get into too much detail on multivariate ANOVA tables where there's more x's in the model. Another thing to calculate, I'm trying to think what else we could calculate. So if I asked you to make a 95% confidence interval for the, so here's a great question here, Chase. Make a 95% confidence interval for the slope of the line. You ready? Try this right here, Chase. Take a moment. You can estimate it. I will take an estimate, but try to estimate a 95% confidence interval for the slope. I will take a very quick estimate off the top of your head. I could guess it right now. I could be like, oh, about this to this. If you don't, I'll tell you my guess. You ready? 26 to 66. Think about how I did that. It's going to be close-ish to that. Close-ish. So 26 to 66 is my guess. And do you see how I did that? I made a 95% confidence roll. I would carry decimals if I was working this on the test. Okay, since it's going to be about not 26 to 66, 27 to 65. 27 to 65. So think about how we're doing that. 27 to 65 is my guess. 27, that rounds to 27, and that rounds to 66. I should have just went with 26 and 66, my first guess. Why am I guessing this? What am I doing? We ended the review, the review last night. That's all it is. You just go whoop whoop, and then go. That's exactly it, Chase. That's what I'm doing. What do you think I rounded the standard error to do it in my head really quick? And I didn't know what these numbers were before I saw it, so I got lucky. But what do you think I rounded that standard error to just be like, well, it's about 26 to 66? What do you think I did with the standard error to just round it like that and just be like, okay, 2 times this, 10. Yeah, that's all I did. And I just did 2 and then just went up 20 and down 20. And then that's the answer. And so that's a big important concept. And this goes back to Stat Tool 1. So I love, especially when Stat Tool 1ers swing by here. And we're talking about, we'll reverse it. If it was a 68, you wouldn't add 1. If it was a 68% confidence interval, then tell me, Chase, before I hit enter, and you do it as a decimal. If it's a 68% confidence interval to estimate not the mean, but the slope, it's not going to be 16 to 76. It'd be what to what. So tell me off the top of your head, just remember it's 10. So instead of a 68 now, instead of a 95, it would be what to what. Like off the top of your head right here, be like, okay, well, it's 10, so about this to this. And then I would follow through on the test and like carry decimals if we ask you to do something like this, to be like estimate. We have wide intervals usually for these. Wow, you just did that. You just did that in your head. And look, it's like decimal place. And then you're like, well, it's about this. So we need to understand conceptually right here and think about what you're learning by using this. And great job, Chase. Another 100 points. Excellent work. Great practice right here. What you're trying to understand is that the standard error is a measure of uncertainty. The standard error is not a good thing. You want your standard error to be as small as possible. It's like I'm telling you, I think the video game will cost about $46, but I could be off by about 10. Now, I'm not saying I'm off by 10. I'm saying plus or minus 10, but it might be like more or less. I don't know. 10 is like my amount of uncertainty. Look at how the intercept has a ton of uncertainty in it. Hence, the intercept goes through 0 and all this stuff right here. And this is basically 0 minus 32 and 0 plus 32. It's not quite 0. It's -2. So -2 minus 32 is -34. -2 plus 32 is 30. So you're seeing the same concept for the intercept right here. The intercept is still just one standard error up, one standard error down because we're making a 68% confidence interval. And then, Chase, you were talking about the 99.7% confidence interval when you said go out one more standard deviation. A 99.7% confidence interval. The numbers aren't perfect because remember, we're estimating here saying it's about this. We also rounded it to 10, but you said, if we go out one more, like 68, 95, 99.7, you're just going out an additional standard deviation or standard error in this instance. So standard errors are not a good thing. They're uncertainty in the estimates of what we're creating in our model. And also the T ratio right here, or T value, is just like the F, where you would take 46 and you would divide it by that, divided by the uncertainty. If you divide this by the uncertainty, you will get 4.796. Did in my head. I didn't. It's the T ratio. So the T ratio is your estimate by your uncertainty, and it has the same concept that the larger the T, Chase, the wider the F. And you can see it here visually. The larger the T statistic, the wider the P value. And I said wrong thing right there for a moment. The larger the T statistic, the what, in terms of absolute value. In terms of absolute value of the T, the F will be wider. The lower the P value. Sorry, I did say F the first time. Chase, you're right. I did misspeak. The smaller the P value. They're inversely related. The F statistic actually cannot be negative because the F ratio is a ratio of positive numbers only, because it's like the mean squares of what was explained over the mean squares of what was not explained. And you can't have negative variation explained and you can't have negative variation left. So the F ratio has to be positive. The F distribution is a positive distribution, where the T distribution is a symmetric normal curve around 0. Not quite a normal curve, but Gossett, long story there, created this curve to expand upon the normal curve, and it has those degrees of freedom. What are you thinking, Chase? This is any questions you got, let me know. But that was a really good review of some slightly advanced topics. But then we see kind of the important like cliff notes of it. Like, okay, if you're making a 68% confidence interval, you just go out one standard error. If you're making a 95% confidence interval, you go out 2. And if someone's like, that's not exact, you say, well, I'll just run the code then. The code will get me the exact numbers, but we should have the concepts that we know of when we build our confidence intervals. That's a horrible confidence interval. When we build our confidence interval, we'd go out 68, one standard error deviation, 95, 2, or 99.7. And we can pick any number in between these, but these are just the classic 1, 2, and 3 standard deviations if we're talking about kind of means and stuff or standard errors. Are there any topics from the exam that weren't covered in detail in the exam review yesterday? I mean, kind of, maybe. Good question right there. I'll probably start looking over the exam a little bit more to make sure I hit up on everything. I would say there's nothing like major. but it's hard. We didn't do mosaic plots. So let's do a mosaic plot review. Let's see. Midterm numeric entry questions. And BS 320 midterm mosaic plot questions. Let's go talk about some mosaic plots. Here we go. So the number one thing we need to know with mosaic plots is what kind of data they take. Chase, what kind of data does mosaic plots take? So a mosaic plot, I'm too fond. We made a really cool graphic earlier. Might be still over here in the viewer. What kind of data does a mosaic plot take, Chase? That's a good thing to know to start right there. A mosaic plot takes, oh, it's so beautiful. A mosaic plot takes what kind of data? That's not a mosaic plot. That is a cool visualization of New Girl search frequency, which we made for class. That's our graphic, our data. I'm gonna go post it later. But yeah, just the increase in frequency. What kind of data makes a mosaic plot? Like, let's make a mosaic plot. Close, Chase, close. If you have a categorical and a quantitative, you're either doing logistic, and here I'll show the answers on the screen, or you're doing side-by-side box plots or some sort of variant of that. A mosaic plot is going to be categorical. So two categorical variables make a mosaic plot, and the numbers in a mosaic plot would be a contingency table, like to visualize the values that we are seeing for how many are in each group. So one of the best codes we have to look through this is going to be the associate function. That's a function in library reg class. Really? Oh, I'm forgetting things today. Library reg class is going to allow us to do some pretty easy and fun things. There's library reg class loaded up, and Chase, great job. 100 points again, Chase. Good practice, good review. Let's load up data, survey 11 today. And let's see right here. We're going to go attach. Now attach attaches these vectors to the global environment such that we can actually look through any of these column names right here. Let's go to names of these names. And there's the names, whether people have broken a bone. Like if we want to go here and go associate, and let's go X46, who's broken a bone. And let's look at it by if they've spent a night in jail. Why not? And people who have spent a night in jail, it's okay. Nothing wrong. Well, I mean, try not to. But they are more likely to have broken a bone. That is strong evidence right there. A very strong statistically significant relationship. Doesn't mean it causes anything. Just means the two are very highly related. I'm just going to remake that graphic again. Someone's smoker. Is someone a smoker? X42. Does someone smoking tell us what their favorite alcohol is? Sure, why not? All the big questions in life answered today. And so now we're looking at smoker versus alcohol, and there is a statistically significant relationship. And really what I'm seeing right here most is that there's a big drop in the none. It kind of is distributed among the other groups, that people who smoke, there's a smaller percentage of them that report that they don't drink. So where people who don't smoke, we see somewhere in the neighborhood of maybe, you might have to estimate around 20-ish%. And we should get those values over here too. Here it is. Of the people who do not smoke, there are 23%, I said about 20, who don't drink at all. And then this is where they're losing, and this is the green one right here, there's 4.7%. Now to find this amount right here, this is called the what distribution. So good question right here, Chase. This right here is a what distribution. So question right here, we'll throw on a little music. That is called a what distribution. You might even say it over there. It's not marginal. This is the marginal. That is the marginal of everybody, the percent of people who drink beer, liquor, none, or wine. That's the marginal. And this is called a what distribution. It is on there. So that's called a what distribution because it's of only the people who smoke. Boom, Chase another 100 points. That's the conditional distribution. And to find the answer right here, so we should know how to find this. It would be of only the people who smoke, of only these people, which there are only 63 smokers. We found them. And of only those 63 smokers, there are only 3 people who say they don't drink. And that should equal up to this on the dot. And there it is, down to the decimal. Does that make sense how that's being calculated right there, Chase? Like we should know, and we always say this, like these are the kind of math questions you might have to deal with. Like you might get output from a contingency table and it might say like compute the expected or compute the cell chi-squared. So we're kind of blending it to numeric answer questions right here. Like if I said, could you compute the expected value of none yes? How would you do that? We'll show it here visually. So compute that value, the value you currently see me highlighting on the screen. Can you compute that value right there? Like find it mathematically with the table. And I can see it. So you should get 13.4. How would you find the expected count of smokers who don't drink? What is the mathematics to find that? And I've got the table to help out. So we're looking for the expected of smokers, people who do smoke, yes, who don't drink. And using the table is really good to answer the question. So it's what is the expected count for people who said, yes, I smoke, and no, I don't drink? How many would we expect? Like if there's no relationship between these variables, I'd expect to see this many. So what is the expected right here? I'll give Chase a moment more, but try to answer this too if you're watching. If you're watching later in the recording, be like, okay, can I find this? Can I mathematically solve this? I'll show the answer. And so the formula we're looking for expected, and you can put this on your cheat sheet, is the expected is equal to row total times column total over grand total. That's RT times CT over GT. If you can read my bad handwriting, I can sometimes read it. So we need to find, remember I said smokers, people who do smoke and who don't drink at all. And we're saying, well, what would we expect? Expected means if there's no relationship, how many individuals should we see here? And we need to highlight of the people who smoke, and watch this. I'm going to highlight it through it this way. And then of the people who have none. And look at what we get right here. This crosses on that number. Now, that's not the answer. But the numbers we are looking for is this is the column total. This is the row total. And we would times those together. And then on the bottom of this, the grand total is this. Does that make sense, Chase? So this mathematically, we'll put it over here on the side. I think we can see the calculator at the same time. Bring it over here. And so mathematically, when you look at this, you're doing 134 times 63 divided by 628. And there it is, 13.44. Chase, how does that look? That is the same answer you see on the screen right there of 13.4. It's just rounded to one decimal, but 13.44. Now, a tougher question is, it's not too tough, but what is the cell chi-squared for this? Which we don't see that answer on the screen to check. But what is the cell chi-squared? So the cell chi-squared is a different formula. Put it on your cheat sheet. So the cell chi-squared, so try to solve this. I want to go to the same one and do the cell chi-squared. Chase, do you know the cell chi-squared formula? I'm on top chat still. Yes or no, Chase, feel free to say, do you know the cell chi-squared formula? So now we want to find the cell chi-squared for that. What is the cell chi-squared? The cell chi-squared formula is, let's go right here. It's going to be observed minus expected squared over expected. And that's a cell chi-squared. I think I did my chi wrong. Sure, we'll do it that way. And that's a cell. There we go. And that's expected cell counts. So expected cell count is row total times column total over grand total. And then cell chi-squared is observed minus expected squared over expected. So the reason you square it is because sometimes that difference is negative. So we want to square them all to make them positive and then standardize by the expected. So it's like, how far are these numbers apart? Let's make it positive by squaring it and then standardizing by the expected. Because think about this, if a candy bar increases by like $1, that's a lot of money. But if a new car increases by $1, it's not a lot of money. So we're going to standardize by what we expect. That's going to give us like a standard to say like, well, what is it generally at? Or what did we expect? Okay, we expected it to be $1 million. Okay, it's $1,000,001 now. That's no big deal. Oh, we expected it to be 10 cents and now it's $1.10. That's a big difference. So the standardizing by the expected is what's going to allow us to give context to this and tell us if this is a large or small change. So we need to grab the observed, which is what we saw, which is 3. We saw 3. It's on there. And since we see 3, we subtract the expected of 13.4. square that. And divide by 3. And great job there, Kenneth. Good to see you here. And so this would be 10.4 squared over 3. Something like, that's like, I don't know what that is. It's like 115. 10.4 squared. I said 114. 108. Divide by 3. Good question. It's actually one question coming up. So the cell chi-squared here is 36. So something seems a little off. Oh my gosh. I saw something in the output and I was like, nope. I divided by the wrong number. There we go. There I see a mosaic. Yeah, good question destroyed here. And hence what we do, I'm gonna click every button. 10.4 squared divided by 13.4. There we go. That is the cell chi-squared. So expected count and expected cell count are different things. No, they're the same thing. This is the cell chi-squared. And Troy, this is good stuff right here. So we use it in other classes, but don't worry. So this is more advanced utilization of it to do a test to see if there is a relationship. So Troy, we can drop a little stats while I want this, because this will also help Chase review. And this is the cell chi-squared calculation, Chase, right there. That's cell chi-squared. Observed minus expected squared over expected. And I'm showing the mathematics with the observed being 3. That's where the observed is at. There it is right there. And the expected is right there. There's the expected value. So here's something, Troy, you'll be learning, and Chase is going to practice right here. If we look at this result, what would this tell us right here about whether or not people drink and what they and if they smoke? Like what people drink and their smoking habits looks to have a what right here. And you can look at it visually. So when you look at it visually, you see, there's less of these people. Hey, Ryan, great to see you here. What do you see visually? Ask any questions you have. We can work on some more 201 or 320. What do we see visually? What does this mean? What does this p-value mean? Yeah. That's what I love about stats. It's very applied. Like we're not trying to solve crazy. It's like, okay, what does this number tell us? Could you help with the activity 6, number 4 on the assignment 2? Yeah, of course. I will go. Let's do that here next. You got it. Great question. Good time to ask. Got a question ready to go. Let's see. I was helping my nephew Tolliver. I got to start off a little bit late because he was trying to get some Nerf blasters going with batteries. What does that p-value tell us right there? And then we'll do the activity next. What does that p-value tell us? Well, it's statistically significant, right? Because the p-value is below 0.05, but what does that mean? When a p-value is statistically significant, it means we reject the null hypothesis. In very simple terms, the null hypothesis here would be that there is no relationship between if someone smokes and people that smoke that have a favorite alcohol is unlikely to. Kind of. If a mosaic plot had differences likely by random chance, Claudia, good to see you here. You got the cyclist. Yeah, let's do the fastest side question after Abigail's question. You got it. A high p-value mosaic plot would look something like this. This might have a p-value equal to, and we could even do this where it doesn't go perfectly. Because the differences between these groups, so remember exactly what you said right there. The differences between these groups look to be what right here, Chase? Like if you have group A and group B, and we're saying if they fail the test or if they pass the test, the differences between the groups right there in the first example, example 1, look to be what? The differences in these groups look to be what? Nice job right there. Yep, I would definitely use, we'll do it here in a moment. You would use jump. I would suggest using jump for it. And the differences between if people take like version A of the test or version B in that top graphic look to be what? Like I have a version A and a version B of the test. The differences between the two groups up here on the top graphic look to be differences likely what? Since the p-value is high, you'd say, oh, the differences between people passing and failing the test. Close enough on top. Exactly. Shreya, good to see you here. Awesome work. Probably like, oh, they're pretty close. Like probably the differences are likely due to random chance. But down here, the differences between these two groups, yes. Oh, wait, did you see Cora? You didn't see it at the start. I'll show that here right next. The differences down here, no, we figured it out, and I should send you the new code. The differences down here look to be unlikely by random chance. And so, Corey, we finished it up. We got it working, and I think it's still on here. Oh, did I delete it off? Is it not appearing here? 2 seconds, Cora. I'll show you here real quick. then we'll do the next question. We got it working. Did I delete it out? Here it is, Cora. There it is. There's the final graphic. We got it working. There's the graphic right there. Good to go. And I should send you this here. But we got it finished after class. We got the seasons. And if you hover over it, I guess on the bottom, it says that, but you can delete the seasons. So it's got that on here right now. It's got the seasons. The line is black. It's hoverable. You can go over and you can see the search frequency of New Girl with all this. So we were able to get the seasons plotted on there and the dates that they occurred. But worked out perfectly. Here, let me do this real quick, Corey. You ready? I'm going to send you this real quick on Discord so you can work with it. Oh, there you go. Wait, I should put in a code block. Oh my gosh, it's a mess, Cora. Here, I'll resend it as a code block. And then we'll do the next question right here. Okay, there's as a code block. But yeah, I agree. That's what we were going for. This is what we did last office hours and during class a little bit today. We made a really cool graphic. Have you already gone over homework 8? We've done some. We'll do a next one. Is there a curve sometimes to the midterm? We'll find out. 320 instructors will talk. So do you know which YouTube videos cover chapter 8 homework? We can do some here next. You got it. We're going to do some activity and then we'll do some homework questions. Let's hop back into it. And great work here, everybody. We're going to do some chapter 8 homework. It sounds up coming up here in a moment. We have a activity question and then let's do homework. And thank you so much, everyone, for being here. Just keep asking those questions. Let me put them down right here. We have BAS 320 activity. Let me find out which one people wanted, and then we'll do some homework questions. Just keep asking those midterm questions, or not the activity 6, number 4. Activity 6, question 4. And then we have the Cycylist questions, Stat 201, chapter 8, Cyclist question. And then if you have more questions, let me know. We can do homework stuff. Let me know. Drop the questions in the chat and we will work on them. I'm going to get the activity pulled up here. But great work. We're back in the swing of things. Back getting ready for tests and for activities, for homework. Okay. I'm going to delete the data. Oh gosh, I've got it saved. Okay, let's go take a look at this. Let me take the timestamp on this. Here we go. We are doing activity 6. For the number on chapter 8, I am struggling to find out the percent increase per year. Which one is it? Which question are you working on, Kenneth, right there? For number 1? Oh, we can do that here in a moment. We'll go back and do some number 1 homework, is it? You bet. 38:15. Let's do the activity. Here we go. Oh, that's nice. I got my major to be BS, so I need my own tier. Kaya, let's do that. We'll put Kaya tier in here after this problem, so stay tuned, Kaya. We'll put in a Kaya tier. I'll let you pick where it's at, and we will put in a Kaya tier. Let's do that. We've got number 6. I'm so glad people like having their own tier. It's a lot of fun. Number 6. Here we are. It may be the case that the correct relationship between the model isn't the measure variable of sale prices and usage, but rather the function of these transformed. Find transformations on your model to see the best fitting transformations. So what we're going to do right here, oh, it's awesome, is we're going to get our model loaded up. We're working with, is it the bulldozer? No, wait, let me find the data we're working with. Sale price and usage, it is the bulldozer data. Data bulldozer. And we're going to go right here and make a model of sale price and usage from data equals bulldozer. 200 points in the chat. If any 320 student can tell me the general format of what I'm coding here to help people understand what the this is, what the this is, what the this is. So 320, really good practice right here to make sure you understand that when we build a linear model, it's blank, tilde blank, comma blank. So 320 practice right there, that anytime we build a linear model, we're going to say the this variable, tilde, the this variable, and then the data equals the data frame it comes from, which these do come from it. Who knows the general format of blank, tilde blank, comma, data equals blank? So what is it going to be if I build my model, which I built some earlier? We'll see people say in the chat. So now that we have this model, we can actually go in and visualize it. So let's go here to visualize model. And here's the visualization of it. Looks kind of not amazing. Boom, Shreya right there. I said 200 points. Y tilde X comma data equals Shreya. Great work right there. Excellent work. And that's worth a 200 points right there. And yeah, it's okay model. It's okay. But what we're going to do is we're going to go to find transformations. And find transformations is going to try different values of squaring, rooting, cubing, logging, all these different things right here. So when we look at the best values of the transformations, oh my gosh, let's do it again. We can see that we originally only explained 1% of the variation. Now we explain about 4% of the variation, and we would have to take our y variable and raise it to the third power. So it says right here, is that the only thing? I think that is, Abigail, was that the only thing? Run on to see the best fitting model. The best fitting model right here is going to be raising y to the third power and keeping x to its regular power. I am starting word to curious maximum points for you to extract capped out. I am at 1 right now. It's 1.2 and the Discord is at 0.5. So the Discord, you can do the exclamation mark. What is it? I don't check mine nearly enough. Rank. You can do exclamation rank in the rank check channel. If I started checking Discord now, is it too late? No, you can still get it. Kenneth, great opportunity. Jump on the Discord. It usually gets more active towards the end of the semester. Oh, you need help for question 4. I think I did the wrong one. Whoops. Question. Oh, you did say question 4. I did question 6. Let's do another break and do question 4. You know what? Let's do question 4 right here. Abigail, sorry about that. I'm going to put another break in the video. And luckily, we did a quick version right there. And let's do question 4. Here we go. You know what? Question 4 would be a great question to do right here. We'll do part of this, and then I'll kind of lead into the rest of it. So, Abigail, if you're stuck on the rest of it, let me know. But we'll get started right here on this question. And we are going to do sale price of a bulldozer on the year a bulldozer was made. Nothing like some bulldozer data. And so first thing you want is to make sure that your bulldozer data is loaded in. If you have reg class going, you'll have the bulldozer data. So now that we have the bulldozer data in, we're actually going to make predictions for certain years. But you have to have a model to make predictions. Now remind me, what makes predictions? The what in a model, think of the LM of it, or the L of the LM. What in a model makes predictions? The what of the model. So we're going to pick the sale price from the year made. That's the X variable. The what of the linear model makes predictions. So the what of a linear model makes predictions. Like visually speaking, the predictions come from the what of the model. So the what of the linear model makes predictions. And this is some good tool 1 review also. We're doing regression too. The what of the linear model makes predictions. And the what of the linear model makes predictions. So what do we see right here? What is the L of LM? So we're basically using a what to make predictions. Not the median. Good guess right there, Abigail. Not the median, but the line. The fit line. Exactly. Kaya, great answer right there. Perfect answer. I'm throwing another 200 points. Everyone participate in good practice the fit line. We're fitting a line to it. That's why we say we fit a line to the data. And that line is what we get an equation of. So we actually need 2 things to make a prediction. We need, so think about back to algebra or geometry. I think it's algebra, right? What 2 things do we need to make predictions? Which this is not going to be fun to write. But if we were to get the 2 values from this, we would need a blank and a blank. Think of the thing back here and the thing right here. To write an equation of a line, we need this value and we needed this value. So what 2 values would we need, which we do see them both on the screen right here. And we have estimates of these values. So think about how the table kind of crosses in on things, telling you this is the estimate of this. This is the estimate of this. So it's saying, here's what I think the value of this is, and here's what I think the value of this is. So we have 2 estimates, and the 2 estimates are for the blank and the blank of the line. So going back to algebra, we would say we have estimates for our year made. What's year made? We have an estimate for the pretty much kind of straight. Good answers right there. The slope and the intercept. You might be saying like y-intercept. So this is the y-intercept estimate, and then this is the slope estimate. It does say x on it, like it says the name of the x variable, but that's the coefficient of the slope. In notation, this would be b1. In notation, this would be b0. So this is b0, the estimate of the intercept, and this is b1. Great work right there, Shreya. Excellent work. So those are the estimates of the intercept and the estimate of the slope. Important we just know what is our output. Now, what we're going to do is we're going to make predictions. So when you think about predictions right here, it's like you want to go out and buy a bulldozer. And when you go out and make predictions for your bulldozer, you actually have to make predictions with a data frame with X variables. This looks like a complicated code, this whole data.frame thing, but just watch this. You ready? Data.frame. What do you think data frame makes? It makes a data frame. So let's go right here and just make a data frame of the letters of the alphabet and take a look. It's just a data frame of the letters of the alphabet. Does this make sense right here that I have a data frame right now of the letters of the alphabet because that's the vector I put in there? Now let's go here and put another value in it of the lowercase letters of the alphabet. And now I have two variables, the lowercase letters of the alphabet. Let's put in another argument and put in 1 through 26 because there's 26 letters and take a look. There's 1 to 26. Have you ever wondered what the 16th letter of the alphabet is? It's P. I don't know. I don't wonder that very much. But with this right here, we're just adding vectors into a data frame. So each argument of data.frame is the vector. I think we give this a name though. This is year made. So when you look at this data frame right here called to predict, it's going to have an X value of year made, or column name, I should say, of year made. We could have done the same thing right here if we wanted to call this numbers. Now when we run this, numbers will be equal to that. And now it's called numbers up there. So we could have named the vector that we're inputting. So we have that right there. It's just called that. The other ones get the name of what they're called. So there we go. We've got our to predict data frame, and this is what we're going to predict. We're going to run a function right here called predict. We're going to make confidence intervals to start. When you run predict, you have to give it something to use to make predictions. So what do you think we should use to make predictions? We'll break this into parts right here. What do you think we should use to make predictions? Anyone got a guess? Like maybe we have something we could use to make predictions. What could we use and where is it stored? Like we could use this. So we'll make intervals. So we're actually going to make these intervals you see on the screen. And then those intervals are going to be created from this. So the fit. I love the answer. The fit line. Exactly. Great answers right there. Teamwork makes the dream work right there. The fit line. So the model is going to make predictions. It just predicts. But the model is predicting for all the values in the model right now. We want to give the model new data. Now, don't let it do the autocomplete, because for once the autocomplete is not our friend. It stored it into M right there, Kaya. Great answer. It's stored into M right now. So our model, that whole thing, that model right there is stored into M. So we can say, hey, make predictions with this model, because we stored the linear model into M right here. We said, here's my linear model. It is going to be called M. So if I'm looking for usage instead of your make, I think so, right? Is yours different? Yeah, if yours is usage, yeah, I just change it. Yeah, so that the whole model there is just the object M. And so you can just say, give me a summary of M, visualize it for me, check to see if it's a good regression. Every time I put in M, it just uses that model as the thing. Or I could say, do an influence plot with it. So I can just do all these different sorts of things with this. Say, hey, make an influence plot of that, make a summary of it, make confidence intervals for me of it. There's the confidence intervals. So I just say, make a confidence interval of this, give me an influence plot of this, check the regression on it, visualize the model. So that's my model right there. That is the model. And so we're now making predictions using the model, and our new data is stored into to predict. And so these are the predictions right here. Now I want you to know something. Watch this though. I want you to know this, that when we are doing these predictions right here, this is... Is that the function? Oh, that'd be awesome. 100 points right there, Kaya. When we are doing the predictions, the very first prediction is a bulldozer made when, which, I think we might have a good stat to one topic here. The very first prediction... The very first prediction is a bulldozer made when. The very first prediction would be for a bulldozer made when. Like this prediction, as I said, predict that bulldozer would be about negative $10,000. They're going to pay about $10,000 to take that off their hands. The very first prediction is for a bulldozer made when. Like this prediction right here. Boom, Shreya, great work. 100 points again. 1965. Nice job, Kenneth. We're going to do some 201 here in a moment. And this is some good practice of 201. The next prediction would be from 1990. The next prediction would be from 2010. The last thing we need to add here is we need to add interval equals confidence. And so this would be giving us confidence intervals for all bulldozers. Now, the problem you get into is there is a huge problem, 201, big one for you right here. The model has a big problem with what? This is why I don't think our intervals are very good down here, because the model has a big problem with what? And I'm showing you by doing this and not doing that. There's a huge problem with the what right here. Like this is not good. Big problem as I do this right here. We don't see this. What am I trying to show you why I don't think it's good? Oh, there is thickness, 100 points there. There is heteroscedasticity. There is plot thickening. It is getting thicker. There's also a big problem with the linear model. Good answers right there, Kaya. There's another big problem right here, and you can see it in especially the residual plot. There's a big problem. Look at the Nike swoosh right there. There's a big problem that it's probably not what? Oh, do you see it? It's curved, 100 points again, exactly. The linearity. And that's why the intervals we have here making predictions, we're actually getting predictions from this interval, and you see how it's negative. Do you see these black bands, which are the confidence intervals? Those values being reported to us for a bulldozer from 1965 on what we expect the average bulldozer to cost is not, the model doesn't go through that data. This is going to be, there's a problem right now because this model is not really well described by a line. Like some of the data is doing pretty well. Like over here, the model's going through, the line is going through the data. But down there on the far side of the model, all the way over there, the model is like not around the data, or the data is not around the model. So this interval is horrible. This is not a reliable interval due to the non-linearity of the model. And so, yeah, that's the confidence intervals. So each of these are the intervals you're seeing on the screen, whether it be for a 1965 bulldozer, a 1990 bulldozer, or a 2010 bulldozer. And then going here, we can do a confidence, I think this is a prediction interval, and just change this to prediction. And there we did it. Now, one thing to know about prediction intervals, and we'll be covering this in class, is the prediction intervals are always what to a confidence interval. So look at your prediction interval, and the prediction intervals are always this to a confidence interval. What do you notice here visually? And Kaya, so many points. Kaya, we're throwing out 500 points. We got to make that level here in a moment. And then we're going to do some more 201 questions. But Kaya just on fire answers. Shreya, too. Great work. Both of you getting some points right there. Everyone getting points. But what do you notice about prediction intervals to confidence intervals? And I'll explain why this is in a moment. The prediction intervals are always what? The prediction interval is this, and we can look at the values. They are parallel, and they have a weird kind of, they slope in a little bit, you can notice here, but they are very parallel because they're around the line. So the line, it's like an expansion around the line. So they are pretty parallel. And the prediction interval is always what to the confidence interval? And here I'll explain why as you think this over. The prediction interval is for one interval. If I change it to usage. Great answer right there. Abigail, great work. You'll change it to usage and then put in the usage values on it. Excellent work. The prediction intervals are always wider. So think about this. If I told you how much money, if you weight tables, which I have, how much money would you expect to get on a $30 bill at a restaurant? Like how much tip? You'd say, well, there's a lot of variation. You might get like $1, or you might get like $8. There's a big widespread on how much will your tip be on $30. But if I said on average for like a whole week, then there would be less variation. Like I said, what is your average tip on $30 over a week? Well, then you're going to get this smaller interval where you're like, well, on average, I usually make like between like, I don't know, on $30, like $5 to $6, about, somewhere in that range. So on average, this is the confidence interval for the average of what we expect for all points, where this individual interval is for just one particular bulldozer. So this is like a bulldozer built in the 1990s on average should cost this much across all bulldozers, but one individual bulldozer has a lot of variation in it. Does that make sense? And good answer, Samuel and Kaya right there. Like this is, I expect bulldozers on average to cost between this and this much if they were built in 1990, that little tiny interval. But then for all, like an individual bulldozer, like I'm going out to buy a bulldozer, it's going to cost somewhere in this interval probably between like 10,000 or something up to like 990,000 or something. So one bulldozer has a lot of variation where the average of all bulldozers is going to have a more tight interval on what we would expect. But prediction intervals are always wider than confidence intervals because prediction intervals are for one individual and confidence intervals are for the average of all individuals. So that's a big concept right here. And Abigail, how are you doing? Additional observations. I think that pretty much covers it. But what other questions do you have? Let's make a Kaya level right here. I'm going to find a good spot. Kaya, how many points do you have? Check your points, Kaya. So I'll make it like right near your points. I'm trying to give everyone different separations, but check your points, Kaya. I might be able to check them too real quick right here. And we'll make Kaya level right here, and then we'll do some. Just we're about to finish the game. Nice job right there, Kenneth. Great work. Go Vols. 100 points, Kenneth, right there. Kaya's checking their points right here. And Kaya's at a little over 100,000. Let me see where the point levels are at. Oh, Kaya's at 101,000. That's so awesome, Kaya. I love we started this new thing of like adding in levels for people. So we need like Kaya level. Okay, so there's Kayla level. Okay, so wait. And it's like Rockstar level is going to be... There's Rockstar level, which... Okay, so Kaya, it's going to... We're going to put in like the named levels in here. People are just going to progress through to different name levels pretty quickly. So let me see. Okay, I'm grabbing it right here. And we'll make it... We're going to make all different name levels for people if they want. Okay, so give me a second. Requirement 101, 1, 2, 3. Okay, submit. I know, right, Shreya? I'm gonna try to like have like it might be really quick. Like, maybe, oh, I'm at this. Like, it's when you get to the 100,000, it's gonna be the fun levels, and it's just my thank you to people who get that many points, get to those levels, and my goal is that a lot of people get to the highest levels, so hence why I just give out crazy amounts of points. But I want it to be fun. And so Kaya, recheck your level right now, and we'll keep adding people in. Rockstar level, it's kind of be a quick level. So Rockstar level is only 1,000 points. We'll see where people are at. Shreya's there at Shreya tier, and we'll see where, because I want to see if Kaya's updated. So let's see if it updated. It probably will update. Let me try. It should update. Let me try points, add plus viewers. Mubot takes a moment to like update every once in a while. We'll hit back to the main screen. Let's do it. We're gonna do some Cycylist questions. So check it again here in a moment. You can just keep checking every once in a while. Talk to Mubot. We've been adding in so many. Yeah, I'm sure you did before me. I'll check it in a few minutes. Yeah, let me know. You've got like a 9,000 point spread between you and like distance between you and the next level. So you've got like 101,000 to 110,000, I believe. That is your zone of points. So we'll try to keep we'll try to we'll add in more stuff. I love it. What's interesting to me, and I asked this in one of my classes, one of the theories was, and we're getting Statue 1 loaded up here, is that this style of learning might skew more towards male learning. But I've noticed that we have so many people engaging on the class, and I've never felt it to be a gendered class. And I talked about that in 201, but we just released a paper, World of Edcraft, and one of the judges who reviews it says, said, is this class, going towards like males? Is it something like, oh, it's gamification, there's points? And I was just thinking about that as like, we've only had, as far as I understand, it seems women so far attending that kind of like, I want it to be for everybody. That's my goal. My goal has always been, this is a class for everybody. You come in, you join in, you have fun. And yeah, also helps with the interaction, especially since it's all is chat. Exactly. And yeah, so I've never felt it's a gendered class. Like when someone says, "Does your class skew towards males?" I was like, I don't think so. But the problem is I only see it from my perspective. Like maybe it does for all I know. But as far as I've been able to tell, and people responded with some really nice emails about like, no, they don't think it does. No one said yes, which I would want to know if someone felt it did. Well, we got the Cycylist question coming up right here. But no, it's so much fun. Like it's a pretty relaxing part of my day to be on here, just working problems. Like it's a bummer when we don't get it solved though. Yay! With that, let's go do the Cycylist question. It is time for the Cycylist question. Here we go. Never. So the Cycylist question is one we're going to need jump for. So with this right here, we are going to connect first off, and so we should be back. Gotta love those random disconnects. Thank you, Suddenlink. And so we have here data on cyclist times from 1903 to the year 2011, And there are some gaps in this data. So we can do a lot of this question except for the parts that we need jump for. And so what you should notice is from 1915 to 1918, there's a gap, or those are the years there are gaps with. And then in the 40s, I think there's a gap also due to the World Wars. There it is, 1940 to 1946. Once you notice that, selecting the right graphic is going to be finding the one with both gaps. This has one gap, not the right data. This one right here has, I think that's both. I think we got it. That's a gap. That's a gap. We're just going to confirm that these don't have gaps. No gap. What am I looking for? I'm looking for a gap in the data where there's no points. And last but not least, this one right here, no gaps. Once again, the gaps we're looking for in the data is when you would say from 1915 to 1919, there's no data right here. And I think it was like 1940 to 1948, there's no data. So the time series is broken. I need Thanos to unsnap. He reverse snaps back. I don't understand. I haven't seen Marvel movies. So let's go ahead and click this right here, and this is the proper graphic. Now, this is where the question gets a little bit weird because there's something going on here. Like if you ignore the start of the series, what do I mean by series? Like all the points in order. This is not really linear. It's got a little wavy pattern, not really following a line very well. But the remainder at the end is following a line. So is there some linearity? Yeah, there's something. There's something. More on that later. But it's not awesome. Everything's not awesome. So let's take a look right here. And there's a positive. Okay, that's not narrowing it down. With a moderate amount of scatter, not narrowing it down. And there are gaps. So now we have to pick between a general linear trend or general nonlinear. I wish they said right here there is some linearity. There's some aspect of linearity. This is true. Hence why we're going to build a linear model. If there was nothing linear at all, it would be ridiculous to do this, but the end of it will kind of destroy the question anyways. But there is something going on right here with the data, and I'll even show you something cool at the end of this. But we need to now take our data after deciding it's generally linear and copy it right here. I clicked the following button, and then I click the following button and copy to clipboard. We're going to hit Control-C or Command-C, Control-C on a PC, Command-C on a Mac, and then go over here into Jump and make sure to open up a new data sheet with File, New, oh my gosh, File, Open, why not? File, New, Data Table, File, New, Data Table. And with the File, New Data Table open, which I'm in, we're going to go here to Edit and Paste with Column Names. Kaya tier achieved. Nice job right there. So we have right here, new rock stars, new all stars in Stat Tool 1. And with this, we are going to then go to Analyze Fit Y by X. And I do want to point something out. Since we're doing a regression, we want to make sure that this is quantitative, quantitative. Nice job. We want to make sure it's quantitative, quantitative. And we do have that because it's blue and it's blue. If it's not both blue, you might have pasted without column names and then it would be red. Start over and repaste it in with column names. Review the video right there. Make sure it's with column names. And then you want to predict the speed of the cyclist based on the year. So make sure you have blue and then you'll be good. So you can see the gaps in the data. You could confirm your graphic. You want to zoom in on it probably, but this is going to be the right one with the two gaps we observed. And now we want to go to the red arrow and go to fit line. The fit line is going to fit the linear model just like LM inside of BAS 320 using R. So this is our linear model right here with the coefficient of the intercept and the coefficient of the slope. This is B0 respectively, B0, and make sure to grab the negative sign. That is an error. That unfortunately, that won't be points back. That is a very important thing. Sometimes I make mistakes, but that would be a big one to not get the negative sign, and then we will need to round it. I would give rounding points back. I always give rounding points back. Round the constant to 2 decimals. So the constant is that one. Round the year coefficient to 3 decimals. Thank you for the inconsistent rounding. There we go. So make sure it's rounded like that. 2 decimals on the first with the negative sign, and then 3 decimals on the second right there. Is the conditions for regression met? No. The plot is not really straight enough. So the relationship is not straight enough. In the early part of the 20th century, they're pointing that out. The variables are quantitative and there aren't any real outliers. We should be good. Yes, we've done it. I always get a little bit afraid. But what I was going to show also is we don't always have to fit a line. You can fit things. Let's remove this. You can fit things that are non-linear. And we will be talking about this in 320. We could fit a polynomial model and take a look. The polynomial model, well, when we go beyond it, it goes crazy. But better yet, let's not fit a polynomial. Let's go to fits. I thought it was here. Fit special. No. Have I lost where it's at? Fit flexible. Fit spline. There we go. Fit spline. And here we go. And there we go. Nice and neat. It might be going back down at the end. You don't want to go too high because that just goes for every point. If we're fitting a spline through, we might get something that looks pretty good. And we do have ways to judge this with things like AIC, Akaike's information criteria. Akaike's. Dr. Bosdogan told me how to say his name properly. And the sums of squares is, of course, going down as we do that. That's actually a 0 sums of squares if we have an R squared of 1. But something right about here might be the true relationship. Don't want to overfit the model. Don't want to underfit it with a line, but you don't want to overfit it with a spline that is too bendy. So maybe that's a much better fit. Go somewhere a little bit less. Sure, right about there. And yep, I know, right? There's so many cool things you could do, and then you could actually use this model to make predictions into the future. Because watch this. We could take our model right here. A lot of really cool, easy things you can do at Jump that you could save your predictions from this model. Like, let's say you were analyzing this data and you had to predict like future trends. So now that we have the data, you could look and make predictions into the year going into the future. So I could just predict for this year. So it's kind of leveled off. Well, I don't know. It's not making any new predictions. I guess I make a flat line at the end because look at that. It's making the same prediction. And the model does kind of show that visually. If you look at the model visually, it's kind of flat at the end. But it's giving the same prediction. It's kind of a bummer. I wanted it to do like, say it's going down. But that is the predictions from the model, and it's saying it's kind of leveled off at this, and it's doing the same prediction. Oh, I guess because it doesn't have any previous data. I don't know. There's a lot of ways to look at this. We could do like exponential smoothing, but we wouldn't be able to go into seasonality because it's yearly data. It also has missing data, so that's interesting too. Yeah. It looks like it's leveled off on how fast the cyclists are going. But just things like this right here, doing predictive models, and notice how the line is probably not the proper fit. And this goes to, we probably wouldn't want to fit a line through this. If you notice, it's kind of neat. You kind of see these patterns. We miss this part right here. We don't get that uptick in the data. But this is the fun part of analytics to me. It's like there's always something more you can do. And yeah, so analyzing the data. Well, back to the main screen. What other questions are there? We're just hanging out right now. We've got open questions. A little bit of fun stuff at the end right there. Some stuff you can do with Jump that's pretty quick, pretty easy. I was like, hey, Jump can do this really quickly. So let's take a shot at it. Let's just take a look. What questions do you have, Kaya, Shreya, anybody in the chat? If you got questions, we got answers. Should we do any of the homework? Could you go over the Scatterplot with A, B, C, D on the quiz? Of course, definitely, yeah. And drop those questions in at any time. Sometimes I'll just go on and on talking about random data. But that's a really good one. I like the Scatterplot. We did the first version of it. Let's do the second version of it. Yeah, I guess the correlation, you bet. When you see the trick to this one, you'll be like, whoa, no way. Let's go check it out. Scatterplots with correlation. This is a pretty fun one. Sometimes I get a little bit afraid, like if it's a question, then I'm like, oh no. But this one we got. Watch this. No fear. I used to have that shirt growing up that said like no fear. No, I don't have it anymore. Blue and red scatterplot dots. And let me change the time. Let's do this. Okay. So when we look at this graphic right here, not that one, what we want to think about is what is the original correlation of the blue dots. So Kaya, what do you think the correlation of these blue dots are right now? Like just ignore every other dot and only look at these blue dots. What do you think the correlation of just those blue dots is? Just the blue dots. I'm going to zoom in on it. What do you think the correlation of just the blue dots are? Only the blue dots. Those dots right there. Looks pretty low, right? Hint on the screen. Probably about 0, right? Which would mean if we put a line through it, 100 points right there, Kaya. I don't want to get you out the Kaya level too fast. They're going everywhere. Exactly. The blue dots alone. So that's what we're thinking about first. The blue dots have a correlation of about 0. Does that make sense? And now let's only add in the following red dot. What would the new red dot right here do to the correlation if we added in that new red dot? Adding in that red dot would do what to the correlation? That red dot right there would make the correlation go very what? That is red dot A, and the correlation would become a lot more this, because it's the furthest out, and it's kind of pulling in that direction. It's going to become a lot more this. It's more linear, and it's going up, right? So it probably, do you have a guess for red dot A on which one it would be? Red dot A is probably the one that is the most what? So red dot A, since it's going up, is probably the one that's most positive. Yeah, that's red dot A. We got it. 1 down, 4 to go. Well, let's use the same sort of theory on E. E over here. You got it, Kai. Excellent work. More points in the chat. E is going to be right there, and E is probably going to make it. If we just add an E, we're only adding an E. E is going to be the one that is most what? And great job, Shreya, too. E is going to be the one that is most what? So E kind of pulls it the most that way. And negative, exactly. So if we go here, what do you think E is? Which one is E? Exactly. There's E. And now D is still a little bit. So D is still like over here, but it doesn't do it as much. So D is also going to be kind of what? D is going to pull it that way a little bit. So D is still a little bit negative, right? So D is probably which one of these? D is still a little bit negative. So D is going to be which one? D is still a little bit negative. So it's negative, and well, there's only one left, right? So D is a little bit negative, not as much pulling on it to pull it in the negative direction. Because when we look at it here visually, it's not going to pull it as far in the negative direction on like a density ellipse. And then now we're down to the last two. Now there's an interesting concept here. C. What do you think I'm trying to draw? C is just going to bulge it out more on that side. It's not going to pull the direction. So C is going to bulge it out on that side. What do you think I tried to draw right there mostly? C is directly in the middle of it. It's on the mean of the x's for the blue dots. What do you think I'm kind of trying to draw a little bit? C and B are definitely the hardest part of this question. I'm trying to draw a what right there? 0. Because it doesn't pull it in the up or down direction. It's just like bulging a 0 out more. Like I could draw a 0 like this, or I could draw a 0 like this, which if I could draw, but these aren't really going in a direction like that. Like that's not a 0. That is some sort of thing. Like that's some sort of 0 that's just a longer 0. And so this is just bulging it out more. So technically, I guess, if we do it by what I'm saying, it should look something more like this right here. It's just kind of bulging out in that direction. It's like, okay, well, it's just a 0 that bulges out on the bottom a little bit more. Still a 0. And so big 0 right there. So C is going to be 0. And it's very, very tiny for the other one. That's what makes this hard, is that this is just, I know it's not outside the dense of the circle, but there's like more pull in this direction due to points. So this one's going to go a little bit more like this. And that has a little bit more of a what direction now, like just a tiny bit, Why is C0? And so B is just a little bit like towards the, like if you extend it further, like this is like the, if you think about vectors and stuff, it has to have some sort of direction on a side where C pulls down on it. So even a point right here would increase it a little bit. Does that make sense? Like mathematically speaking, like C pulls down on the, because it's right on the middle of it. It's in the very middle of the circle. Like mathematically, they made it the mean of the circle. So it's pulling down on the circle where the other points are on a vector pulling it in a positive direction. I can show you here visually inside of R, because this is the biggest. Don't worry, we don't go this conceptual on the test. This is definitely a tricky conceptual one. Core demo. If you look right here, if we make the same graphic sort of, we're trying to make a box close. You see, it's very hard to make an exact. There we go. Almost. Oh, no, negative. There we go. Okay, now that I've got a box on the screen, if I go right here, you see how it remains 0? But if I go over here, it's going to pull it in that direction a little bit. But if I go closer to the center, it's going to pull it less. But the further away I go from the center, the more it's pulling it. You can see it's now actually adding some pull. It's like more dots on that side pushing it out. But if you go right below the mean of the box, as long as I'm on the mean of the box, which is the mean of the x's. Like if you average this together, it's just going to pull it down. Or if I went up here, it's just going to pull it up, and that's just decimal change. It's meant to be 0. Now I can't get 0 anymore. But as long as I'm doing things mathematically accurate, it will do that. Oh no, I lost. Yeah, there we go. So there we go. If it's right at it. Yeah, so it's a big conceptual thing. That's the hardest part of this question is this one gives a slight pull up, and that one that's directly below the mean would not do anything to those points. It would not change it. Good. It's a tricky conceptual one. It also would impact r squared and stuff like that. So remember, r squared is just r squared. More questions. I might grab some food here before class, but we'll hop back. What questions are there? Let me know if you got them. Near the mean will be, so what it is, and this is a good conceptual question right here, but I don't think we put it on to 1. Near the mean of the x's, there is small leverage. This is a well beyond concept, Kai, right here. I'll bring up some stuff to show it. So, 2 seconds. This is a big concept. It actually goes to how influential a point is. So, oops, I need to finish this. End. Okay, so let's do, I'll mention 320 right here. So 20 seconds back. 116, 20. Figured out how to, yes! Send it to me. Send it to me. Yes. I love it. I love it. Cora, 100 points right there. Thank you so much, Cora. You're doing great. I have fun making that kind of stuff. Influence and leverage. Okay, so this plot looks all kind of crazy right here. I might need to go to something smaller. Let me make a much smaller linear model. So I'm going to try to bring this into like 201, 320. Are you into cars at all? Because I'm not. So this is a cars data set with the horsepower of cars based on the weight of a car. So we're looking at the horsepower of a car based on the weight of a car. Does that make sense right here? Awesome, Cora. Does this make sense? Like, here's the weight of a car in tons, and here's the horsepower of a car. Yeah, I know. Well, hopefully this makes sense with like 201 kind of merging the topics. Does it make sense? Oh, you're also not into cars. That's what you're saying. Well, that's how much the car weighs. And that's how much the horsepower of a car is. Now, what do you notice about cars that generally weigh more? Like, you would just generally say to me, cars that, awesome. Cars that weigh more generally have a higher horsepower, right? Now, the cars that are going to be most like influential in this model would need to be a car that is far away from the model and a car that also is far away from the mean of the x's. The mean of the x's for this model is going to be probably somewhere in here. Does that make sense? If I said the mean of the x's is there, Kaya, yes or no? Does that make sense? If I say, I'm just guesstimating, be like, oh, if we average the x's, that's about where the average of the x's are. So that's where the average of the x's are. Awesome. So we have this concept called leverage, which, think of it like a seesaw. Like if I were to jump on the seesaw over, let's put 2 me's. I do it this way when I teach leverage. If I were to jump on the seesaw right here, it wouldn't do much. But if I were to jump on the seesaw over here, it would do a lot. Like this is small leverage and this is large. But leverage works on the other side of the seesaw too, where you could still have large leverage over here. I need a head. So that is also large leverage. Leverage is defined as how far you are away from the mean of the x's. This is what you're seeing with the other question in 201, is that when you're right below the mean of the x's, you have no leverage. So if I add an additional point right here, you're just pressing down on the seesaw. You wouldn't move the seesaw, you would just move the intercept. You would move it downward. So since this has no leverage, like in your example in 201, it's not actually going to bend the seesaw in any direction. What we can do is we can make what's called an influence plot. Now it's going to look crazy right here, but what I'm going to do is, visually speaking, I'm going to fold this graphic over because leverage is only a positive concept. So now the graphic's been folded over, and these are the high leverage points. There's 1, 2, 3, 4, which are probably the points of those 3 right here. And are those 3? They're slightly below the line. Those are the 3 right there. And then there's only 1 point, that point right there, which is, yes, slightly above the line. So, oh, awesome. Yeah, that's how I like to explain it. It's just a seesaw. And it's really tough. This graphic's a lot of times hard for people to understand right here, like what's going on with this, because this is the thing folded over on top of itself. So all these points right here that have no leverage are where? Shreya, great work right there too. So if you understand this, you might understand this graphic decently. Every point right here that has leverage close to 0 is where on the original graphic. Every point, I'll disappear, that has leverage close to 0, these cluster of points right in here are points that would be near the what? Because they have very little leverage. Like this is their amount of leverage. You can only have positive leverage. Like it's only, awesome, Cora. Every point that has very little leverage would be a point that is very close to what? And so think conceptually over here on the other side of the graphic. They're near the mean. That's worth some 200 points right there. They're near the mean of the x exactly. So, and then which side of the mean they're on doesn't matter. It wouldn't matter if they're on the left or the right side, because if they're over here, it doesn't matter if they're over here. It's just how far are they away, and that's what leverage is. So these 3 points right here are these 3 points right here, and that singular point right there is actually the singular point over here. And if you look visually, that point should be about visually the same distance away as those points. It confuses people because the graphic's folded over on top of itself, and then you're seeing, it's just hard to look at a lot of times. And then these are the deleted studentized residuals, and we're still talking about concepts like residuals, because a residual is how much you miss by. And I'll end with this. A deleted studentized residual is basically a what score? So this is good because 320 hasn't even covered this yet. Think of this. We really care if it's outside of -2 or 2, where we'd expect 95% of them to be. A deleted studentized residual is basically a this score, because it's like, it's extreme if it's outside of -2 or 2. I'm going to try to get one that shows... That's it, Kai. It's a z-score, basically. It's basically a z-score. And we can see if there's extreme points right here. Do I have Survey 10 loaded up? I don't. It's a z-score. It's a deleted studentized t-score, but or studentized, but it's a z-score. I go into greater detail on why I basically call them z-scores. But you can see right here the boundaries of -2 and 2. And then these points right here, we would say have undue influence. These points have too much influence. And then we can find out which observations these are. These are the points that are very far away from the model, because things on the model would have a residual of 0. So, and these are the points that have high leverage. So points that are influential are very far away from the mean of the x, and then they're very far away from the model. And you can see these points, like this point down here, that extreme point over here, is going to be that extreme point. Ooh, just barely not influential. Wow. That's crazy. That point is barely not influential. I think it had to be. Wow. Shocked. Barely. And then we've got that point over here. That point has to be that extreme point up here, because it has such a high value above the line. Its residual is just crazy. And then you see it right here. And then there should only be a cluster of points further away. Is that visually making sense? There's the points further away that are closer. 1, 2. That's about right. I think so. There's a bunch of cluster points. Anyways, that's got it. We'll be back. But those are some advanced concepts. If you understand this to any degree, you're doing excellent. These are advanced concepts, and we go through them step by step and explain what these topics are. Until then, we're going to start some 320 here in a moment. I'll see everyone later. Bye for now. Bye. 320 coming up soon.